thank you so much for joining us today. We are going to be going over lesson 4.03, which covers single and double replacement reactions. There must be some mastery of previous material required. Okay, so we need to stop for a second. We have to really make sure that we look at that. Are you sufficiently prepared? In 4.03, we do see double replacement reaction. A double replacement reaction is where we have two compounds, and I have listed them as AY and BZ. The individual letters just represent an ion. Okay, keep in mind that we always put metals first. So A and B are metals, Y and Z are either nonmetals or polyatomic ions. Because with ionic compounds, we always write metal first. So AY is some ionic compound, BZ is another ionic compound. Now with double replacement reactions, what happens is that the metal of the first compound will form a bond with the nonmetal of the second. Okay, notice how we get AZ. The metal of the second compound will form a bond with the nonmetal of the first compound. I'm going to highlight these as well. And notice we get B and Y. Please notice that the metals are always written first. So how do we know if something is an ionic compound? Is that you have a metal bonding with a nonmetal. When we're predicting our products, as you noticed, we have to form new compounds. Let me back up a slide real quick. These are new compounds. These are made by combining these ions. Well, guess what happens every time we form a new ionic compound? We must write the formula, which means we need to know what the common charges are in order to know what formula will be created when A reacts with Z. That's the 3.05, 3.08 coming back. Remember in 3.08 we saw this periodic table with the common charges, and we just find on here our element, and at the top it tells us what charge it is. Now remember, the elements in the middle of the periodic table, okay, these transition elements, tin and lead, these are what we call the special metals, and they take on more than one charge. So these metals are the ones where it could be +1, +3, +4, +5, just kind of depends on the metal. So you might want to go back and review the special metals to remember how to form those new compounds. But if you're one of the main group elements, you can just look at this periodic table and you will be able to tell what the charge. Here's our list of polyatomic ions. This is from lesson 3.08. Please make sure that you save that. I would recommend printing it so you can look at it. You will be using this the remainder of the course. There's 5 types of double replacement reactions. We are actually going to work through them all the exact same way. Okay, sample problem number 1. We see magnesium hydroxide, and this is, we could call it hydrogen phosphate or phosphoric acid. Now we have the hydroxide, the hydrogen. Okay, the important part for now is to realize, okay, we have a metal and a polyatomic ion. Uh-oh, we don't have a metal here. But that's okay. It still can be considered an ionic bond because the hydrogen forms a plus charge, phosphate forms a minus charge. So hydrogen, he's a sneaky guy. He can act like a metal with regards to electron configuration and the common charge that it forms. And so what we look at here is the element, the first element in the first compound is going to form a bond with the nonmetal or polyatomic ion in the second. So what we have to do is figure out, okay, what formula is going to occur when those two hook up, so to speak. So we must look at our table of common charges. We see that magnesium is in group 2, so it forms a 2+ charge. Phosphate is a polyatomic ion, and it forms a -3 charge. There are A couple of different ways that we can write this final formula. I like to employ the crisscross and reduce method. What that is where we write down our elements. Okay, we have magnesium. Phosphate is a polyatomic ion, so I'm going to go ahead and put it in parentheses. And then I just crisscross the charges, just the numbers. So we crisscross and reduce those new subscripts. Well, 3 to 2 cannot be reduced. That's our final formula, Mg3PO4 2. This part right here was very challenging for you. That's 305 and 308. You must go back and review those two lessons. If you have a different way to get the final formula, that's perfect. You do not have to do it the way that I've done it here. Some students do use a different method to get the final formula, and that's absolutely fine. So our second formula is going to be the positive ion of this compound forming a bond with the negative ion of that one. Just keep in mind, do not look at this subscript unless it's a polyatomic ion. The polyatomic ions stay together. PO4 is the phosphate group. That had to stay together. OH is the polyatomic ion. So that is going to stay together. So we get hydrogen and hydroxide. Do not copy this 2 over because it might not apply anymore. The 2 is because of the charge of magnesium. So we look at just the ion. This ion is just hydrogen. This ion is just hydroxide, OH. So now we look up on our periodic table. We see hydrogen's in group 1. It forms a +1 charge. Hydroxide is actually a polyatomic ion. So all we do is look at that list, and we see that hydroxide has a charge of -1. And what this means is that it just requires 1 hydrogen and 1 hydroxide to be neutral. Okay, remember, ionic compounds form to cancel those charges. Now, HOH is the same thing as writing H2O. If you wish, you can leave it as hydrogen hydroxide, or you can rewrite it as water, H2O. In chemistry, we always have to have a balanced equation. And I'm actually going to leave water as hydrogen hydroxide. I like to make a table to help me balance. I can keep my polyatomic ion together because hydroxide appears the same on both sides. PO4 appears the same on both sides. So I just list my elements. Now, if this is confusing, you can just list everything separately. Magnesium, oxygen, hydrogen, phosphorus. So I'm going to write down the total number of everything on each side. So when we look here, I need to balance everything. I'm going to start with magnesium. If I put a 3 out here, then remember that 3 is going to get distributed to everything in that formula. So I have 3 magnesiums. Now this part can be a little tricky. Hydroxide, I have a 2 here. So that means I have 2 hydroxides for every formula, but I have 3 formulas. So 2 times 3 equals 6. Okay, once again, if you have a subscript after the parentheses, that subscript gets applied to everything inside the parentheses. So I have 2 hydroxide for every formula of this chemical, but I have 3 formulas written. So 2 times 3 equals 6. Okay, next we go to hydrogen. I have 3 hydrogens here. I need to have 3 hydrogens there. Not a problem. Let me just put a 3 there. Now that is going to change the number of hydrogens and the number of hydroxides. So I end up with 3 hydrogens and 3 hydroxides. My hydroxide's not balanced yet. That's okay. We can come back to that. Okay, let's go ahead and do phosphate. Phosphate, I have 1 over here and 2 over there, which means I need to have 2 on the left side. So I'm going to go ahead and put a 2 in front. Now remember, that gets distributed to the hydrogen and to the phosphate group. So I now have a total of 6 hydrogen. Remember, the 2 gets multiplied by the subscript. So that's 6 hydrogen and a total of 2 phosphate groups. Okay, so it looks like my only problem is this hydrogen hydroxide over here on the right side. I have 3 right now, but I need to have a total of 6. So what I'm thinking is, well, instead of having a 3 there, what if I put 6 there? Then I would have 6 hydroxides and 6 hydrogens. And there we go. We are balanced. Let's work through sample problem number 2. Again, we see the first element forms a bond with the second chemical. That's the new material to 4.03. Okay, magnesium is going to form a bond with the sulfate. So what we have to do is figure out, okay, what formula is that going to form? So we see MgSO4. Well, looking up on the periodic table, magnesium has a 2+ charge. Looking up in the sheet of polyatomic ions, sulfate has a -2 charge. Now we can do that crisscross and reduce like I did last time. So we bring down just the numbers, and we see Mg2SO4 2. If we look at just the subscripts, 2 to 2. Well, ionic bonds actually form with lowest ratios. So it's actually going to be MgSO4. Now remember, SO4 is the group, so don't look at that subscript in terms of trying to reduce. The subscript that you're looking at is SO4 with the 2 after it. Let's move on. So we have MgSO4. Now our next chemical we see is hydrogen forming a bond with phosphorus. Remember, positive ion always is written first, so it's hydrogen forming a bond with phosphorus. We look up at the periodic table and we see that hydrogen has a +1 charge. The common charge for phosphorus is -3. So we can do our lovely crisscross. +1, so that's just a 1. -3 is 3. H3P1. And usually when we have a subscript of 1, we don't write it. And so now we just need to balance. So balancing, we have 3 magnesiums here. I need to have 3 magnesiums over here. That causes me to have 3 sulfates. I need to have 3 sulfates. I now have 6 hydrogens. I need to have a total of 6 hydrogens. Don't forget, that also changes the number of phosphoruses or phosphides. So that's 2 of the phosphide ions. Look at this. We already have 2 here. So we are now balanced. For this problem, I would like for you guys to pause this recording, write this problem down on a sheet of paper, and go ahead and write the full, complete, balanced equation. Don't forget to look at your common charges and your polyatomic ions from 3.08. Do the best you can, get as far as you can, and when you have it done, or as far as you can get, then resume this recording and we'll work through it together. Double replacement reaction, we see ionic compound, ionic compound. We know with double replacement reactions that the first element is going to form a bond with the second, either ion or polyatomic ion. So we know aluminum is going to form a bond with CO3 carbonate. Carbonate's a polyatomic ion, so if you want to, go ahead and put it in parentheses so that that 3 doesn't mess you up. A lot of students see this 3 and they start trying to change that 3. You cannot change that 3 as carbonate is the CO3 ion. Okay, now we look up on our periodic table of common charges. We see aluminum has a 3+. We look up on our list of polyatomic ions and we see that carbonate has a charge of -2. Remember, polyatomic ions act as 1 unit. So this is kind of like if you were to think of X with a -2. Okay? Don't think of it as carbon and 3 oxygens. It's just carbonate. Just imagine it's X. Okay? Don't let that 3 mess you up. Okay, so now what we can do is crisscross and reduce our numbers. So we get 3 to come over here, 2 comes over there. 2 to 3. I can't reduce that at all, so that is my final formula. Al2 CO3, since it's a I wrote the wrong number. CO3, since it's a polyatomic ion, has to be in parentheses if we need more than one. You might be asking yourself, well, what if we didn't have the parentheses there? Does it really matter? The answer is yes. Because let's say we did not have that parentheses there. Look at that. We would end up with 33 oxygens. Do we really want 2 aluminums, 1 carbon, and 33 oxygens? Absolutely not. We want 3 of the carbonate groups. Now we need to form the formula for the second compound. And remember, it's the positive of the second compound forming a bond with the negative of the first. And so we get K and Cl. Look up on the periodic table of common charges. We get K plus. Cl is a -1. We have a 1-to-1 charge, so it only requires 1 of each element to be neutral. Remember, ionic compounds form in order to have an overall charge of 0. +1 -1, I only need 1 of each ion. When we crisscross, we get 1 and 1, and of course, we don't write 1s for substitution. Now we need to balance this lovely equation. If you want to use that table, feel free to go ahead and pause this recording, pull up that lovely table, and go ahead. And since we see carbonate, CO3, CO3, we can keep it together. And if we keep it together, then we see that we have 1 carbonate on the left side and 3 carbonates on the right. We have 1 aluminum, 2 aluminums. Let's go ahead and start balancing that. I need 2 aluminums on the left, but don't forget that changes your number of chlorines. I now have a total of 6, because each chlorine here has a 3 after it, so that 3 gets multiplied by 2. That means I need 6 chlorines on the right side. And remember that your coefficients go in front of the whole chemical. Do not put it here in the middle, because that'll change the chemical. So it's 6 here, so that's 6 potassium, 6 chlorines. But I only have 2 potassiums here. That's okay. If I put a 3, 3 times 2 equals 6. And now I also have a total of 3 of the carbonate groups. So 3 carbonate groups, 3 carbonate groups, and we are now balanced. So let's do a quick summary. So in summary, double replacement reactions, DR, double replacement reactions, 2 ionic compounds, and basically they just are switching partners. So we must know what 2 ionic compounds look like, metal and nonmetal. So remember that ionic means you have a metal plus a nonmetal, or a polyatomic as we saw in these examples. That's how you know what an ionic compound is. Now we're going to move on to single replacement. Single replacement, though, is where we have an element and a compound. So instead of having 2 compounds, we have just an element by itself and a compound. And what's going to happen is this first element is going to come and it's going to try to replace B. It's going to try to kick out B. Let me rewrite that arrow. And A is going to try to form a compound with Y, just like we saw before. And the difference with single replacement is that since A is by itself, it has to form an ion. So we have to look at something new called the activity series in order to determine if A is reactive enough to form an ion and to form a bond with Y. Okay, so in the lesson for 4.03, you will see the activity series. I recommend that you go get that if you don't already. Print it because you will use it for all single replacement reactions. Lithium's on top, and then it goes down. Now what this means is the elements on the top are super, 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 super active. So if you have an element like lithium and it's going to try to break up a compound, it's going to. So the activity series, the elements on the top are super reactive. The elements on the bottom, for instance, Au, which is gold, not so reactive. So we see 4 basic types of single replacement reactions. The first type is when a metal replaces a metal. Now what happens is sodium is going to try to come in and form a bond with sulfate. When a metal is by itself like this, it is the pure metal. Sodium, which is a solid. It's not an ion already. So what has to happen is sodium has to form an ion to form a bond with sulfate. So what we're going to do is we're going to look up sodium, the element that's by itself. It's right here on the activity series. And we're going to look up copper. Copper is right here. Notice this activity series has most of the elements. I didn't include all of them at the bottom because I took this from the course. So what we want to look up is sodium, the element that's by itself, is it more reactive than the element at the beginning? Because remember, we're trying to replace copper. Is sodium higher than copper? When we look at this, yes, it is. What that means is that this reaction will occur. That's all we need the activity series for. Some single replacement reactions do not occur, so we have to figure that out first. Because if a reaction does not occur, there's no sense in writing our products because they don't exist. So we must, with all single replacement reactions, and only single replacement reactions, we must look at the element that's by itself, see if it's higher on the activity series than the first element in the compound. If it is, then the reaction will occur. Sodium will form a bond with sulfate, and now we're going back to the 305 and 308 where we have to write that formula, just like we did with double replacement. Sodium is in group 1 on that periodic table of common charges. Sulfate has a -2 charge in our list of polyatomic ions. I'm going to put sulfate in parentheses because I want to make sure that my polyatomic ion stays together. And we get Na2 and then SO4. I only need one of the SO4 groups, so that's the formula. If you wish, you can leave sulfate in parentheses. That is okay. And then for my other formula, it's just copper. Because this is only a single replacement reaction, so what this means is that copper goes off by itself. So we just get plus Cu. Now remember, whenever we have elements by themselves, we have to check for those diatomic elements. Remember those diatomic elements? Okay, those diatomic elements, that's actually an E, even though it doesn't look like one, does it? Diatomic elements are the elements that when they're by themselves, they always have a 2 after it. Okay, now remember, this is when they are by themselves. Okay, not in a formula, just by themselves. These are the diatomic elements, and if you notice, they're non-metal. When we're looking at single replacement reactions, you're going to have an element that goes off by itself. Please double check to make sure that it's not a diatomic element. Okay, so single replacement reaction is when we have an element combining with an ionic compound. That's how you know it's a single replacement reaction. Okay, here's an element by itself. reacting with an ionic compound here. Okay, that's metal replacing a metal. Now what we do is we see, okay, zinc is going to try to come along and form a bond with chlorine. So what we have to do is look up zinc on the periodic table, or excuse me, I'm sorry. We have to look up zinc on the activity series. Okay, so let's go ahead and highlight zinc. Zinc is right here. Let's go ahead and highlight sodium. Sodium is right here. So the question we must ask ourselves is zinc higher than sodium? No, it's not higher. Means zinc is not reactive enough to replace sodium. So we write no reaction and we're done. Because if there is no reaction, it doesn't make any sense to write products because the products don't exist. So anytime the element by itself is not higher, no reaction. Think of the elements on the top, they're like the bullies. They're the bullies of the single replacement reaction. Type number 2, we have a metal replacing hydrogen in water. Honestly, we work through it the exact same way. Nothing new. If we have sodium and you see H2O here, remember that H2O is the same thing as hydrogen hydroxide. HOH. Remember that? Okay, so the sodium is going to try to replace H. Okay, so we look up on the activity series. We look for sodium. Sodium's right there. We look for hydrogen, which is right there. So sodium is higher than hydrogen. It will occur. So then sodium is going to form a bond with the hydroxide. And when we look at this, we see sodium has a +1, hydroxide has a -1. And so when they come together to form a bond, it's just NaOH. And then hydrogen is going to come off by itself. And remember that hydrogen is diatomic when it's by itself. Remember those diatomic elements. Anytime you have hydrogen, chlorine, oxygen, fluorine, bromine, iodine, anytime you have those elements by themselves, not in a bond, it's always going to be with a 2 after it. We also see some smaller reactive metals. We're actually going to form the oxide. This is where things are changing just a little bit. We have one of the elements that are not really reactive. We're going to actually form the metal oxide instead of metal hydroxide. So we have to have the right conditions, and then the lower ones will be able to react. We have aluminum, zinc, iron, all these elements that are down here. So basically, we're going to get the hydroxide if it's a alkali metal, which is what you learned in Group 1, and even Group 2 on the periodic table. Remember, we learned a long time ago what Group 1 and Group 2 is on the periodic table. We learned what alkali metals are, alkaline earth metals. That's all old stuff for Modules 1 and 2. If you're not sure what those are, definitely go back because you got a semester exam to do. If you have any other metal other than a Group 1 or Group 2 metal, it's going to form the metal oxide. So that zinc plus water forms zinc oxide plus hydrogen gas, because the zinc is going to come in and form a bond with the oxygen, and then hydrogen goes off by itself. Look at the second example, gold. Gold is actually on the bottom of the activity series. If you have the one printed from the course, you can see gold on yours. It's on the very, very bottom, and it is under hydrogen. If it's under hydrogen, it's not going to replace it. The third type of metal is when we replace the hydrogen in an acid. Lead is going to try to come and form a bond with chlorine. So we have to look at the activity series and tell. Remember, it's always the element by itself trying to replace the hydrogen. We have to look up on that in the activity series. We find lead and hydrogen. Look at this. Lead is just above hydrogen. But you know what? It's above it. As long as the lead is above it, it will occur. So lead is higher than hydrogen. Lead is going to form a bond with chlorine. And I believe in the activity series in the lesson, it goes through and it shows you that lead would form a 2+ charge because it's one of those special metals. Chlorine forms a -1. When we do the crisscross and reduce, we get Pb1Cl2, which remember we just write as PbCl2. The hydrogen is by itself, so it's H2 because it is diatomic. Don't forget about that. And then now we just balance. Okay, notice that even though this is type number 3, we worked through it the exact same way. So far, really the only thing that's special is when one of the lower metals react with water. That's really, so far, the only one that is special, that does something special. Okay, the fourth type is actually a little bit special also, because the fourth type we're going to see a non-metal. It could be a non-metal replacing a less active non-metal. So what we need to do is we need to find fluorine and chlorine. So fluorine is higher than chlorine, so we're going to get sodium and fluoride to come and form a bond together. NaF, because sodium forms a +1 charge on the common charges. Fluorine forms a -1, so it's NaF. And remember that chlorine is one of the diatomic elements, so it's Cl2. So don't forget, those diatomic elements are all by themselves. Last step, we need to balance. We see 2 chlorines on the right. We need to have 2 chlorines on the left. And then we have 2 sodiums now. We need to have 2 sodiums here. And now that we have 2 sodiums here, we now have 2 fluorines. But that's okay, because we have 2 fluorines here. So our final balanced equation is F2 plus 2 sodium chlorides forms 2 sodium fluorides plus chlorine gas. And again, it's very similar, but in this case, since this is a nonmetal, it's going to replace the nonmetal. Okay? And then we look at this, and this is actually from the course itself. So go to the course 4.03, scroll down to the section where it talks about the single replacement reactions, and it says types of single replacement reactions. Click on nonmetals, and you will get this picture. Let's do some practice. Our first example is going to be calcium plus water. Remember, these are single replacement reactions, so we must look at the activity series. We must look to make sure that calcium is higher than hydrogen in order to actually have a reaction occur. So let's look at the activity series. We see calcium, we see hydrogens way down here, so that means this will occur. Calcium is one of those metals that's in group 1 or group 2, which means it's going to react with water as if it's hydrogen hydroxide. So calcium is going to form a bond with hydroxide. Calcium has a 2+ charge. Hydroxide has a -1. So when we crisscross and reduce, we get CaOH2. Hydrogen is going to come off by itself, so that's +H. But don't forget, hydrogen is diatomic, so it's H2. Balance this real quick, and there we go. Just put a 2 in front of water, and it's balanced. Number 2, we see zinc plus iron sulfate. So let's go ahead and see if we can find these. So let's find zinc. Oh, there's iron. Where's zinc? Where's zinc? Where's zinc? Zinc is on this one, right? Oh, there it is. Okay. So is zinc higher than iron? Yes, it is, which means zinc will form a bond with SO4. Okay. In the activity series in the lesson, I believe it has the charges for those weird metals, those transition metals. 2. Sulfate has a 2-, which means it's just going to form ZnSO4, because 2 to 2 means that we only need 1 of each. Iron is not a diatomic element, so it's just written as Fe. And the cool thing about this reaction is that it balances itself. And the last one we see is bromine reacting with calcium chloride. Now we got to look at bromine, and we have to look at chlorine. Is bromine higher on the periodic table than chlorine? And it's weird because with the nonmetals, it actually does follow the periodic table. Bromine is lower than chlorine, which means no reaction will occur. So write no reaction. Do not write your products because there are no products. Nothing forms. If you get a beaker and you put bromine gas in there and calcium chloride, nothing happens. In summary, with single replacement reactions, remember it's an element plus a compound. We must use the activity series. We have the activity series with metals, and then we have the activity series with the group 7A nonmetals, those halogens. Okay, make sure you have both of those and that you'll use both of those depending on which problem you have. If the element by itself is higher on the list, the reaction will occur. Write your products using your common charges and polyatomic ions if they're included. And then don't forget your diatomic element knowledge. You must have those diatomic elements when they're by themselves. If the element by itself is not higher on the activity series, then write no reaction and move on. Thank you so much. It's been great working with you for double replacement and single replacement reactions. Please take advantage of all the other recordings that we have. And don't forget that you can use the recordings to review older material and when you're getting ready to study for that semester exam. The recorded sessions are extremely helpful as you're reviewing for the semester exam. Come into our live teaching that we have each week for older material as well to stay current so that when you get to the semester exam, you're not having to relearn an entire course at last minute. Thank you so much, and I look forward to working with you next time.